All right. Hello, everyone. Welcome to On .NET Live, where we're going to have 60 minutes of unscripted .NET entertainment. Our mission is to empower the .NET community to achieve more. I'm your host, Maira Wenzel, with my co-hosts, Frank Boucher and Katie Savage. And today we have Aaron Stannard. Welcome, Aaron. I know he has a lot of goodies that he's been working on. Like he was talking about his demo before we joined. And sorry, John is not here. Surely that we don't have John today. He usually is on the community stand-ups for ASP.NET. For those who really like to see John Galloway. But Aaron, how about you introduce yourself?
Sure thing. Hello, everybody. My name is Aaron Stannard. I'm one of the creators of Akka.net, which I've been working on it in some way, shape, or form since like late 2013. So Akka.net's a pretty mature open source project at this rate. I've been working on it full-time professionally for over 10 years now through my company, Petabridge. So yeah, that's that. I kind of have my fingers in a lot of different pieces of Akka.net. The stuff I mostly work on is the distributed systems facets of it. So clustering, remoting, all that good stuff. But that's kind of the basic gist of it. And then our little wherever we want to kind of take the meeting today, I'm going to be kind of focusing on how to put all this stuff together to build like a real application and talk about how actors, which is what Akka.net's all about, how that kind of enables you to build different types of software than what you'd be able to do with just good old-fashioned stateless web APIs. So we're going to go ahead and build like a real live interactive Blazor server application using actors as kind of the key players in that whole system. So yeah.
All right. Do you want us to share your screen or should we start with that?
Yeah, why don't we start with that?
Okay.
Okay, so I think I'll start with just kind of showing a little example of what actors can do, and I'll also take a look at the source code, and I'll kind of work my way backwards to the sort of more basic facets of it. So if you've never heard of the actor model before, this is actually a super old computer science concept that dates back to the early 70s. So I think the actor model white paper came out in it was either 73 or 74. And this was a vision that computer scientists had for being able to do large scale, concurrent computing back when they were using, cathode ray tube powered mainframes that took up a living room size space. The actor model white paper, never really came to fruition until people started building more like internet scale systems in the 1980s. Ericsson and Erlang was kind of the first real commercial implementation of it. But now there's actors everywhere in lots of programming languages. Every major runtime has them. .NET's got at least 3 or 4 different actor implementations running around. So it's a concept that's gained a lot more traction, primarily because it helps with cloud computing. There's a big sort of facet of it that makes actors very economical. But the real reason why people should be interested in actors is they enable you to build real-time applications. So not just CRUD, where you're kind of are making changes to objects via post and put verbs. This is more for things that are a little bit more high fidelity than that. So let's take a look at an example. So the example I'm going to show here, let me go ahead and get both of my browser halves up and running. Let's see, I got one. Let me grab the second one. Should be, I guess, here. There we go. All right, to kind of really make the selling point here, this is DrawTogether. Now, this is an open source reference application that I've been working on for a number of years. Kind of originally started it when I was doing a Twitch stream pretty frequently, which these days, I have a father with 2 young kids. They don't get time to stream in the evenings anymore. But I've still been kind of working on it and using it in some of our YouTube videos and some of our other let's say just sort of reference materials. So this is DrawTogether. Now, if I go and create a brand new drawing and I pick a little color stencil here, by the way, this is all built using Mud Blazor. Fantastic project if you want to get into building Blazor applications. And let's say I go ahead and draw, I don't know. I'll go ahead and do a little stick figure here. Now, I'm not a particularly talented artist, so hopefully no one will hold that against me. In fact, yeah, it looks like I'm gonna kind of make him into like a. It looks like he's kind of sitting cross-legged almost. Maybe we're doing hot yoga with this stick figure. All right, so that all looks well and good. This is all built using, yeah, like I said, Blazor server, and this is basically a big scalable vector image is what we're producing using these strokes and pens. Now, by itself, this does not look like this. Looks like Microsoft Paint with fewer features so far. Where Akka.net comes into the picture is I can take a look and see what are all the active paint sessions that are happening on the server right now. And I can say, oh, there's one active user in this paint session. Let me go ahead and join that. And I'm going to get fully synced on whatever this person was drawing. I can go and create my own stencil. Let's go ahead and play around with the cursor size a little bit here. And I don't know, maybe I'll go ahead and irradiate them. So do something a little bit more fun and frivolous like that. And you can see the actual drawing state being synced in both locations here. And I could do this, I could scale this up to hundreds of people all working on the same drawing. I don't think it'd be very intelligible from the point of view of the individual end user to try to have that many people all scribbling together, but the system could definitely support it. And this is an example of something that we can power with actors. It's the two-way synchronization that's happening. And on top of that, actors are actually solving a couple of more subtle problems with this Blazor server application than just the synchronization of content between servers. I'm actually also using my actors to solve my old version of this app. If I fire this up, this is the version that I've got running in like our private environment right now. Let's see, I should be logged into it. Yeah, here we go. This is the old version of the application as of like last Thursday. I made a lot of changes to it in preparation for coming on today. But if I go and grab a pen and I draw some lines, see all those big dashes that are showing up there? That's actually caused by the way Blazor samples the mouse move events when we're going through here, where it leaves kind of little small gaps in the mouse event rate sampling that's going on here. One of the things we're using Akka.net for is we're kind of correcting this on the server side by keeping track of the last known position of everyone's most recent stroke. And we're making sure we basically kind of interpolate those lines to make sure those gaps don't get closed properly, so the line looks fully connected. We also have to make sure we don't hold the line. If a user is holding down the mouse and drawing it continuously, we want to make sure that we're emitting little chunks and little stroke objects while we're doing this. Otherwise, no one will see anything until the user releases their mouse, and that would be no good. So we kind of needed to make sure we could do a little bit of both here, which is release little chunks, but make sure those chunks still look like a fully contiguous line later. That way you get that full interactive, rich experience. So that's kind of like the big picture thing for what actors are doing here is they're solving some backend issues, they're doing some synchronization work, and they're doing all of this with very, very low latency. The other thing that's cool is that these diagrams are actually fully persisted using Akka.persistence on the back end, and they're also event sourced. So I could, if I wanted to, implement like an undo or a redo buffer on here and allow people to pop strokes off the stack and then put them back on again if they want to, just like how you'd expect to be able to if you're working with a local desktop application. Akka.net has a built-in sort of a event sourcing structure for how it does persistence that would support that without me needing to add a bunch of extra functionality. So that's kind of like the broad strokes, no pun intended, of my little application that I built. Let's talk a little bit about what actors actually are and what they're doing. Or before I dive into that, are there any questions maybe?
Yeah, there is one that I think will be connected to your actor's explanation, which is like, are you utilizing event-driven architecture for this with RabbitMQ perhaps? So it's like, maybe it ties into like what actors are and what they're doing behind the scenes.
Philip, you have set me up perfectly for the next part of of actually diving into the source code here. Couldn't have done that any better. Thank you. So I'll go ahead and pull up the DrawTogether source code here. I'm going to shut down .NET Aspire real quick. All right, so let me go and close all the tabs real quick and kind of talk a bit about actors and how they get events. Because yes, Philip, this is an event-driven architecture, but we actually don't need external infrastructure like Rabbit to do this. Actors natively communicate via message passing, and we're doing this all with just pure C# is how all of it works, and F# also would work as well. If I go to my DrawTogether repository here and we go down to our actors, let's take a look at the local drawing session actor. All right, now I'm going to go ahead and close some of these. These are some internal message types here that I'm going to go ahead and get rid of real quick. They're mostly used for basically pairing the actor with the SignalR connection that's powered by that the Blazor hub uses. All right, this is an actor in Akka.net. We inherit from this base type, untyped actor right here. There's other different actor base types you can use. We'll see another example of one in a moment for a persistent actor. But this is sort of your basic actor type here. And the way actors work is they have a method called onReceive, which takes an object as an argument. And this is where messages get handled. All actors fundamentally are just message processors, and they can have state, which this actor definitely has a bunch of. And basically, every time a new message comes in, we inspect that message's type. We maybe inspect its content as well, and then we make a decision about what to do with it. And all of these types right here that I'm handling inside the switch statement are different either events or commands that I have built inside my application. So let's take a look. For instance, this is a brand new event type I just added on. I think I did this on Friday. And let's take a look up here. So one of the things that I do when I'm trying to compose and knock it on an application is I basically define a messaging schema, more or less, or maybe a messaging taxonomy. Kind of depends on whatever flavor you want to use. Where I have an interface, I paint session message, and this has a canonical identifier attached to it. And the identifier in this case is, as my very helpful comment explains, user who did the thing. So we have a user ID. And this is the same user ID that we use inside ASP.NET Core Identity inside the system. So it's basically referring back to the same user. And then we have another interface here, I drawing session event. And this correlates to a drawing session ID, which is basically just so this is like a value object. It's just a string-based identifier for being able to specify what drawing session this is. If you
Which
have
is the
multiple,
one that you were showing on the screen, right? Like you had the two sessions.
yes. Well,
Mm-hmm.
both those users were actually technically in the same session, working on the same canvas together. So the drawing
Yeah.
session ID kind of like identifies the canvas. The paint session message identifies the user attempting to make changes to it. So it's like a two-part identifier. Basically, you have the drawing and the person doing it. And so this interface has a number of different inheritors here. Now, you probably can't see this all that well. So let's go and take a look at one of them here. We have this class. Let me go and close my annotations here. Add points to connected stroke. So when I'm holding the mouse down, and I'll show you the Blazor code for this in a moment. When I'm holding the mouse down and dragging it over that SVG surface area, Blazor is emitting potentially hundreds of these per second inside the system. And so it's emitting all of these connected stroke events. And what it's going to give me is a point, which is an XY coordinate where that stroke is. And it's going to give me these two identifiers. And then we also have the stroke width and the color that is supported by the drawing surface here. So this is just a real simple data object, right? We don't have a unique identifier for this point because transmitting thousands of points per second, if you have multiple users all drawing, and persisting them in a database is a super inefficient way of trying to build an application like this. We absolutely don't want to do that. So if you've been building, let's say, native apps before, like WPF, or maybe you've been doing mobile, you're probably already familiar with this technique. But if you're a backend developer, you probably aren't. We're going to use a technique called debouncing with Akka.net to go ahead and basically take all of these points, and we're basically going to transform them into a line. And that line object is going to be what we persist. So, and that line's not necessarily just a beginning and end. It's actually a curve is what we're going to persist. So we're going to store all the points and then render it as an SVG curve object in Blazor. So this is an example of one of the types of events that comes in here. And that event will be sent. I'll kind of walk backwards to the Blazor code to show where the event comes from. But this event gets sent to this local drawing session actor. And this is another kind of key point about the actor model. Actors are really cheap resources. They don't use a lot of memory, and they don't use any CPU if they have no messages to process. So it's very inexpensive to have a bunch of them. They are not expensive resources by any stretch of the imagination. So typically what you do in order to keep things simple as a programmer is you want to have one actor per entity inside your system. So in this case, we have a local drawing session actor. This actor runs on the Blazor server instance where at least one user is currently connected via the Blazor hub. That's the built-in SignalR connection that Blazor server has. So this is interoping basically between Akka.net and also other actors running on other machines and the local SignalR connection. Now, here's the really cool part. You, as the Akka.net developer, do not need to know or care where those other machines are, whether those other actors are in the same process as you, or anything else. Akka.net will transparently make sure those messages get from point A to point B for you. And we'll see a little example of that in a second. Now, this local drawing session actor correlates to this drawing session ID. Messages come in. So we have these two in particular that we care about. Add point to connected stroke and then stroke completed. This is an event that we emit when the user releases their mouse. It means they're done drawing. Therefore, any additional points that get rendered should belong to an independent stroke from this one. It's basically just something we're doing on the back end to kind of make sure the whole chart gets, or the whole drawing gets rendered correctly. We'll talk about this guy in a second. And the rest of all these messages right here all do pretty basic things. We have a user joining a paint session, leaving a paint session. These events happen when either a user connects to a specific URI in Blazor. So if I pull up, I shut my application down, but when I basically load this page right here, that's going to go ahead and trigger the join drawing session. That's going to tell Blazor there's a user active in this session. When I navigate away from that page, that'll create a leave paint session. And then there's also a button I can use to basically completely nuke the drawing and start from scratch again. That's what that is there. Clear drawing session. That's going to erase all of the SVG points that we've drawn so far. Now, this is all basically the message processing side of things, and I haven't even shown the state or any of the other actors we're talking to yet. Let's kind of take a little look at where we're getting any of these events from. What's the actual input source for these events? That was kind of the second half of Philip's question. Well, this is my Blazor page, paint.razor here, and this is all, like I said, using Mud, Blazor, layout, and components. If I scroll down here, this is sort of our toolbar. This is where we're basically creating the color picker and allowing people to slide the cursor size. And we have our little button for clearing the screen. And then this custom Blazor component right here, the drawing surface, that's where we actually render the drawing. That's also where we record the mouse input events. So if I go here, we basically have all of our different mouse events kind of correlate to some event handlers on here. We have our SVG, and we have some basically custom points for doing rendering. This circle basically is going to show you where the user's mouse is right now. And this curve is going to take all of those debounced strokes that I'm going to pull out in just a second and renders them as a straight up curve. And I think this is also a custom object here. Yeah, it is. Down here is all the view state. So we have, and by the way, this is being rendered for a specific user in their browser. So we have their user ID. We have all the strokes that are inside the system right now. We have the current cursor size and color. And then we have all these event callbacks right here. Well, what's going to end up happening is if I scroll down just a little bit, when we do on mouse down, we start invoking these callbacks. So we go ahead and we do a transform. We have to do a little bit of transformation because this UI is responsive. Based off the size of your browser, we have to go and turn that into an XYZ coordinate to fit inside the SVG. This is all front-end stuff, which if you're a back-end developer listening to this, you might feel bored and disappointed by. No worries. We're not gonna stick around in front-end land for very long. But when we go ahead and we invoke this callback, that's going to end up invoking a callback method defined in, it should be, let's see, here we go, on point added. What we're doing is we're grabbing this local actor and we're doing actorref.tell, and we're just creating a new add point to connected stroke message and sending that to that local actor. And this is an asynchronous operation, even though it's void. It's a fire and forget messaging system is what we have here. I tell the actor a message, and when the tell method exits, all that it guarantees is that that message has been queued inside that actor's mailbox. Every single actor in Akka.net has a built-in thread-safe mailbox. And the way actors work as a message processor is they work by processing the messages in that mailbox one at a time. The real big advantage of working with actors from a thread safety and concurrent programming standpoint is that any changes you make to an actor's internal state are automatically guaranteed to be thread safe, because that state can only happen sequential. Those state changes can only happen sequentially, which is we process messages in first in, first out order. We can't process multiple messages concurrently. Akka.net's mailbox is designed to not allow that. And therefore, if I want to go and add an item to a dictionary or resize a curve in an SVG, I can do all of that without having to deal with locks or semaphores or anything else. It just works.
And
So
are the SVG, like, are you saving the, I don't know, the coordinates and like where you should go? Like, I'm curious in terms of, like, I never work with images, but I'm just curious in terms of like making the drawing appear, and well, how are you saving that?
So on the front end, it does that translation for us because the SVG is a relative. The whole point of it is to be a scalable vector graphic, right? So all the points are basically relative to the size of the SVG. So that little
Mhm.
translation we do on the front end gives us like a reliable reference point we can use. We then have another Akka.net component I'm going to show in a second, our debouncer, which takes all those data points and basically debounces them and then compresses them into a line. And then that line gets broadcast to everybody who's connected. Like, we basically have our own like lightweight SignalR backplane, essentially. That's all powered by these actors. It basically broadcasts those lines out as they're being persisted. And all this machinery is running with extremely low latencies, like under 5 milliseconds per, like basically 5 milliseconds, probably for groups of, let's say, 10 to 20 strokes at a time, depending on how much drawing activity is actually happening.
And I think
And
that goes to guacamole guacamole question. Is latency a big issue between actors? So the answer is no.
the whole point of actors is to not have high latency. So when actors are messaging each other in memory in Akka.net, on this machine, I'm running like an Intel NUC. So it's a relatively low powered CPU, but it's kind of recent. I can do something like 8 million messages a second between two actors in memory. So that's very fast. Going over like a single TCP connection, max possible speed for, let's say, these messages were all being saved as like compressed, compressed using the natural, let's say, sparse format of protobufs. I could add gzip compression to it, but it would be pointless because these messages are so small. I could probably transmit those messages somewhere from 500,000 per second over a connection to maybe 750,000. It would really kind of depend on how quickly the serializer could work in that system. So the latency is designed to be very low between these 2 points. So when I'm doing all that drawing on screen, if I go fire up the demo again, let me actually kind of show you a little bit about what's actually happening on the back end. If I go back, so this is the input right here. In my little Blazor page, if I scroll up to the top, I'm using a bit of dependency injection. We have this thing called an IVE required actor, and this will give me a reference to a local drawing session actor that will go ahead and be made available on the fly. So I inject this local drawing session actor into here, and then let's see, here we go. I go ahead and I basically resolve it asynchronously, just in case actors get spun up asynchronously on the back end. This is just in case, in a very rare case, where somehow the Blazor page managed to start up faster than Akka.net. There's, in a practical sense, no way that could ever happen. Akka.net will be completely done initializing in like under 50 milliseconds. And by the time a Blazor page hits the load balancer health check, it's probably been a second or two with all the jitting and everything that has to happen. So there's no way that could happen. But because I like to deal with uncertainty, this basically means I'm going to wait until that actor's available before I start trying to message it. That's all this means here. Even though realistically, the actor will always be there by the time this Blazor page starts up. So I'm going to go ahead and get a reference to my local actor right here. And I'm going to go ahead and start doing things like, this is how you can do request response with an actor, by the way, which is I can go ahead and ask, hey, I want to send you I want to get a local handle for this local drawing actor right here. I want you to go ahead and send that back to me. And basically this will use a little request response. I've got a cancellation token on it. So if you don't want to do fire and forget, if you need to wait for an actor to respond back, ask will let you do that. And the way ultimately the way this task gets closed is the actor that received this message has to reply back to the sender. That's kind of sort of how we close the circuit there. Let's see. Sorry, before I keep going, I know I'm moving through a lot of code. Are there any questions?
There are a couple, Aaron. One of them is coming from David, and he's wondering, since debouncing is a common algorithm, how are you implementing it in Akka?
Oh boy, that's a good one. So we're using a technique we're using a library called Akka Streams. Let me go ahead and shift over to that. So I haven't even gotten into the distributed system stuff yet. This has all been local actors so far. One of the things that we have inside Akka.net that I'm a huge fan of is Akka Streams. Now, what Akka Streams looks like, this is actually some Akka Streams source code right here, but that is not the debouncer. If I go down to, here we go. This is our debouncer right here. So Akka.net actors have the ability to run some code before they begin processing messages. And that's what I'm doing here in this little pre-start method. So I'm going to set a receive timeout. This is like an idle timeout. If this actor hasn't received a message in 20 minutes, it means that the user has probably stopped doing anything on their tab, but they haven't closed it. If they close the tab, this actor would get destroyed via some of the Blazor code that I wrote. But if they just walk up and attend a meeting for 60 minutes, then this receive timeout will kick in and it'll kill off this actor. What I'm doing right here is a little bit of Akka Streams code. And let me maybe rearrange this to make it a little easier to see. In fact, I'll put this on a new line. Akka Streams looks a lot like LINQ from a syntax standpoint. So I'm going to create the first, and also the other thing with Akka Streams is it's fully type safe. So I'm going to create a source. This is an input object for Akka Streams. And this is going to be a source.actorref, which means that I'm going to compile this Akka Streams event source, and it's going to give me an actor reference back and then an untyped source. That actor reference is how actors communicate with each other, and it means I could take this source and pass it around over the network if I wanted to, or to other actors in the same process as us. Doesn't really matter. And I'm going to stick that in this debouncer field. And then I have this little extension method I wrote right here, source.toConnectedStrokes. And this is a little bit of reusable Akka Streams code I wrote. I wrote this so I could unit test it. Is basically why I kind of extracted it into its own library or its own helper method. But this right here, this operator, is how we do debouncing. It's called a grouped within statement in Akka Streams. And you can think of it like a batching operation that operates off two different heuristics. One heuristic is how many items are in the group. And here, I think we've defined a default batch size of 10 items. And then our default batch window size is 75 milliseconds. So as you can imagine, if someone's moving the mouse around, they're generating strokes at actually a fairly fast rate, right? So 75 milliseconds isn't that long for that. If we were doing debouncing for something like periodic network events that are arriving, you'd actually would probably want a higher threshold for that rather than a lower one. But because UI events come in at such a fast clip and we're trying to make things seamless with the render on screen, we're going with a low timeout on here. Grouped within says, I'm going to emit an array of my input items. And the input items here are those paint session messages. This is that event-driven protocol we talked about earlier. I'm going to basically construct a batch of either up to 10 elements or as many as I can find in 75 milliseconds. And then the next Akka Stream stage below me is going to get that set of output. So I'm going to convert that into an immutable list. I then have a custom Akka Stream stage I wrote to do that interpolation between the strokes. That's what this does down here. So this is kind of a custom stateful stage I authored. And then we're going to just take all those connected strokes and process them one at a time, turn them into these drawing session commands. This is what we need to persist them on the server on the back end. And then if I go back here, this is us actually transmitting them to the server is what we're doing. We're going to take this drawing session actor right here, and we're going to ask it to process this command within 2 seconds and then give us a result back. If we caught an exception during the processing of that command, we will go ahead and just emit a failed result out downstream here. And then finally, at the very end of my Akka Stream, you can define an Akka Stream sync as, well, we have syncs that write out to SQL Server, or syncs that can write out to a database or to Kafka or to a CSV file. In this case, our sync is just a for each loop. We're just going to go ahead and just kind of write it out down here. And mostly we're trying to log warnings is all that we're doing. With this type of application, I don't want to blow everything up because the command failed to get processed. The worst thing that can happen is a stroke doesn't appear on the screen. And so we're just going to kind of keep chugging along if that stroke doesn't appear. So this application is, if you're a distributed systems person, it's lower on consistency and higher on availability on the CAP theorem side of things there. And that's because it's Microsoft Paint, dude. Like, no one cares if you miss a stroke on there. So that's why it's
I care, Aaron. I care.
Like I said, my test audience for this is my 2-year-old and my 3-year-old. They might really care. So I'm going to have some pretty strict quality control people coming after me in a bit here.
That's perfect.
So question from Philip, just to clarify debouncing, was that to handle the Blazor inability to capture all of the on-screen rendering? So I had a GitHub issue that I just closed on Friday, or maybe I closed it on Saturday. I don't remember. But long story short, we noticed a big performance drop in Blazor server's rendering speed when we upgraded from .NET 5 to .NET 8. This was last year sometime. And so we hadn't changed any of the Akka.NET stuff at all as part of that. It was just straight up a .NET runtime change. And we think it had to do with how Blazor server was sampling some of the mouse events. Mouse move in particular was the one that we think was the source of the problem there. So I had a couple of different options for how to solve that problem. One was to try to like call into the JavaScript runtime and capture the mouse events there. And I was just like, bro, that's way too much front end dark magic for me. I'm just going to do some math on the back end with Akka.NET and solve it that way, which ended up being like not as hard on the UI and the render loop. And it was easy to verify via testing, which is another thing that I thought was useful. So the debouncing stage kind of serves two jobs, Philip. The biggest thing that it does, if I go back here, is that if I go down to the bottom, this is my custom stage. We're solving that math issue with Blazor, but the biggest thing is we wanted to take all those points and construct them into a line. And this code that I'm about to pull up here, let me find it. Here we go, process batch. This is using a little bit of link down below here, where we take a look at this list of paint session messages. We're going to group all the points by user. We're going to create a set of connected strokes. And then for each of the points drawn by a user, 2 users can't draw the same line. That's just not possible, right? So that's why we group it by user first. We iterate through each of these, and we basically construct a line for each of those points. We have some code here, and this is my math for dealing with like the missing stroke. Basically trying to check to see, did the user change the properties of that line? So if they change the color or they change the size, then there's no way these two strokes can be connected. It might mean that we've missed a stop stroke event, which can happen. Sometimes the browser won't fire some of those events reliably. This is kind of a synthetic way of us detecting that. And then at the very end, though, yeah, JS interop is so fun. You know, we had to do some JS interop to deal with the resizability of the window. We had to do some for that problem, but I wanted to avoid doing that for the mouse events. Wanted to try to stick to as close C# as I could. And then we have a little threshold calculation for, do we think these lines are continuous? I set it to a fairly high value. I could tune this down if I wanted to. And that'll mean that basically the lower this value is, the more likely we're going to create a new line is what's going to happen. So it's kind of a little threshold check here. I liked making this tunable. So the biggest thing that this code did before I added the code for doing interpolation on, well, not really interpolation. It's really just remembering the end of the last stroke and setting that to be the beginning of the next, end of the previous stroke, setting that to be the beginning of the next stroke. That's the math that we're doing. It's not anything fancier than that. No real interpolation or whatever. But that was something new that I added. The old code basically just took the points and compressed them into a line. That's what we call a connected stroke inside this system. If I pull up that data structure, it's basically just an array of points. And we keep the whole array of points, but we persist it as one object. So rather than trying to persist hundreds of points, it gets saved as an array of 100 and gets rendered as a stroke of 100. That's what allows those lines to have curved shapes, is we basically have all those different data points kind of rendered on it. So this is all the fun front-end stuff on here, which is dealing with the debouncing of all the events. And just to kind of scroll up a little bit, the way those events get debounced is we feed them into this actor here. Every single server has at least one debouncer processing strokes for all users working on the same diagram on the same machine. So like I said, if you have 3 machines and hundreds of users, there'll be at least basically one instance on each machine of this actor doing the same type of processing. Where things get fun is the distributed systems piece of this. By the way, before I jump into that, are there any more questions I should try to address?
Yeah, there was one. I think it's been a while since we have this type of question. So, what's the theme you're using?
Oh, I'm using, I think, the classic Rider Dark theme. I'm turning 40 this year, so I've developed a little bit of photo sensitivity as I've started to get a little older here. So I had to get rid of all the light theme stuff. This is JetBrains Rider's default theme. Default dark theme, that is. Let me double check actually. Let's go to IDE settings. Theme. Yeah, there we go. Rider Dark. That's the default.
Voila. So now we know.
There
were some questions as well about like the backend in terms of like wondering if there's no socket being used. Or Philip was asking if it would try to make sense to try UDP. So I don't know if you want to talk a little bit the behind the scenes.
Sure. So let me dive in a little bit to the backend stuff. Yes, we are using sockets and we're using TCP by default. So this is and by the way, if you guys want to see the source code for this, let me go ahead and grab the repository link. This is all open source.
Oh, I shared the link, but yeah, let's share it again.
Yeah, definitely. So this is all open source. You guys can pull the guts down. It's all licensed under Apache too. If you fork it and turn it into a commercial project, just promise me you'll buy a support plan later. So yeah. But no, that's it's all available to look at. So most of this is all Blazor and ASP.NET stuff for the most part. But if I go down here, configure Akka. Here we go. This is using a library called Akka Hosting, which is basically Akka.NET's integration with the entire Microsoft.extensions ecosystem. So it supports dependency injection, logging, config, health checks, hosting. It's probably another one I forgot. But yeah, basically all the good stuff here. If I scroll down, this is the real meat that we're putting on the bones here. This is this add Akka method that we add to the service collection. And down here, we're kind of building up Akka.NET's configuration. So we have persistence. We're configuring that. I have a custom serializer I wrote in Protobuf. That's one of the things that we're going to be automating in Akka.NET 1.6, which is the new version we're working on. And then we also have configure network down here. So the way this works is we're turning on Akka remote, and then we're turning on Akka cluster. And then these two components down here, Akka management, we're not really using it when we're running it locally on this machine, but like my old version that I'm running on a live server, that's running in Kubernetes. And this allows us to go ahead and perform some service discovery using things like Kubernetes labels. I'm going to try to add support for using the Azure storage discovery system as well, which will use like a Azure table for all these nodes to find each other. You don't technically need service discovery to build an Akka.NET cluster, but I find that it's actually helps simplify configuration quite a bit and particularly in live environments. So that's kind of why I'm incorporating it into this sample here. But if we take a look at the config that we're using, let's see, am I using just the default configuration for this app? I think I am. Here we go. Yes, I'm using the default config here. So this is just a little POCO class I put together, and I parse this out of Microsoft.extensions.configuration. And I have my remote options where I'm just going to say, look, our host name is going to be whatever the current machine name is, and then we're going to run on port 8081. And then for our cluster options, we're going to go ahead and basically form a cluster with ourselves. So we're going to use a static seed node system to do this. I could go ahead and basically add an array of nodes if I wanted to have multiple nodes all running at once, or I could just use that Akka management config to do that. So that's kind of what's powering the whole networking side of stuff here is Akka.remote and Akka.cluster. Akka.remote uses a dedicated TCP socket for communicating back and forth between nodes. So if I pull up my browser here, if I go back to my system 76-1, I actually have 3 different nodes spread out across our 5-machine Kubernetes cluster here that are all working together to do these drawings. So works fine in a scaled up setting. Locally, I'm just using whatever I can spin up in .NET Aspire, which right now is a single node cluster. So that's how that's all kind of working behind the scenes. Now, the clustering piece is really interesting. Let's take a look at, I'll go back to my code. Here we go. So the clustering piece is really interesting. When you create an actor by default, so if I take a look at, add local drawing session actor down here. I know what the problem is. If I go to implementation, it's because I already have that window open and it's this source code, I think, down at the bottom. Yeah, here we go. We're calling builder.withActors, and we're basically creating a local actor by calling actor system to actor of here. By default, when you create an actor with Akka.net, that actor is just local to the process that you live inside of. It's not going to magically change because you turn on remoting or clustering. Instead, what we're going to explicitly configure is, let's take a look at this drawing session actor right here. This actor is our backend actor. It's the one that synchronizes the data for all the local actors that are running throughout our system. So there's only one of these for every drawing. And we're using a technique called Akka.cluster sharding right here, which basically is very similar to Orleans virtual actors, if you're familiar with that concept at all. So we basically are going to declare, we are going to create a shard region of type drawing session actor. And this is how you create a drawing session actor using this little function right here. And then we're going to specify a little bit of config. Drawing session actors can only live on nodes that have this label, this role right here. It's basically a way of kind of identifying, if I have a heterogeneous cluster with multiple different process types all cooperating, it's basically saying this process hosts this actor. That's all that does. And then we pass in a little piece of code right here that tells us when we message this shard region, how do we uniquely identify an entity? And in this case, we're just looking for that interface and we're extracting the session ID off of that. So this is kind of how you basically extract an entity ID from some of the messages you send to the shard region. When we create a shard region, that's going to distribute these actors evenly all throughout the cluster, and it guarantees that there can be, at most, one globally unique instance of each drawing session actor ID at any given time. And we guarantee that even when there's problems on the network, like if there's disruptions happening or computers going down, cluster sharding will continue to observe that guarantee. So this is kind of a system that values consistency ahead of availability in a lot of cases. So if we take a look at this actor, you'll notice this actor is using a different base type than before. This is an untyped persistent actor. What that means is exactly what it sounds like. This actor persists its state using Akka.persistence, kind of another part of the Akka.net framework. And if we scroll down here, we have a persistence ID property that we have to override. This is kind of like half of the unique identity of Akka.persistence. And so we set that persistence ID to be equal to draw session - session ID. That will kind of uniquely identify this entity inside the event journal. And we're using SQL Server for our data store in this case. But you could also use Azure Table and Blob Storage. You could use Redis, MongoDB, and virtually any other flavor of SQL Server. I think there's even some third-party plugins for things like Google Bigtable and Cosmos DB running around as well.
In your case, what are you using?
SQL Server 2022.
Okay.
I might shift it to Postgres because I can actually get this thing to run. Basically, we're using Entity Framework and Akka.persistence, which are both completely database agnostic. So I can switch to Postgres if I want to. And I already have a Postgres instance running on my Raspberry Pi where I plan on hosting this in my home lab. So might go ahead and just reuse that. But SQL Server is working totally fine as well. And both of those databases have great support with .NET Aspire, which is another thing I would consider. So down here, this actor has a state object, this drawing session state. We maintain a dictionary of all the different strokes that we've processed. This is how we can do some debouncing on the server side if we need to. If somehow we got a duplicate copy of a stroke, we could basically just ignore it if we wanted to. We also have a mutable hash set of all the users currently in the chat session right now. That's what powers that home screen when we see the total number of users that are in the drawing session at any time. And then otherwise, the rest of the data is basically just a timestamp and a little Boolean that indicates whether or not this drawing is not in use anymore. So this drawing session state is going to get modified every time we process a drawing session command. And I have a little extension method I wrote here, process command, where basically we're going to go ahead and take an add stroke, remove stroke, clear strokes, add user, remove user, pretty basic looking instructions that we're going to send to our actor that's keeping track of the entire drawing state for all users, right? Well, what this actor is going to do is we're going to process that command. And if that command basically was not able to be processed successfully, or it didn't produce any events, we go ahead and we just tell the sender hey man, you made a mistake, and then we don't do any further processing. But if we go down here and it looks like we do have some events, we tell the sender right away that we successfully processed their command. And then here's the real moneymaker. We call persist all async, which is going to basically make a round trip to our database, persist all of the events as a batch. And then for each one of those events, we're going to publish them out to the subscribers. And then we're going to apply them to our state. Our state's an immutable object. So we're going to go ahead and basically side effect it this way. We're going to update it in response to each of these events. And for every 100 events that we persist, so this is 100, not in a batch, but like cumulatively as this actor's been running, we're going to save a point in time snapshot of what this total drawing state looks like, which is what we're doing here. The whole purpose of doing a snapshot is that if you have a really long-lived persistent actor in Akadot persistence, you do not want to be replaying hundreds of thousands of events every time that actor needs to start. That is going to put a lot of strain on your IO system, and it's going to take a while. So one of the ways we can kind of reduce our load time is by saving a snapshot periodically, which says that, and because the way the Akadot persistence recovery formula works, if I close this is how we recover state when this actor restarts, or if the actor got killed and recreated on another node, this code would run first before the actor processes messages. The first thing we do is we load the most recent snapshot we've taken. And only after that do we load all of the events that were taken after that snapshot. Akadot persistence provides a very robust versioning scheme for state. And basically the snapshot goes first, and then the events taken after that snapshot come second.
So does it mean when you do the snapshot, does it kind of like attach all the lines together?
It's
so like you have only one, and then like after that you'll have the other segments or lines.
So what it's going to do,
lines, I think he said.
Yeah, all these connected strokes. What it's going to do is it's going to save this entire object as one big binary blob using protobuf basically. And then we're going to go ahead and retrieve it back and forth. So it's not going to go ahead and like, let's say, merge the strokes together. That's another optimization I could in theory do, is do a little even more back-end aggregation for like persistence. That'd be another potential change I could do. But for the time being, it's just going to go ahead and save this all as basically one big representation here. Now, these objects are fairly sparse. Even if I have 30,000 of them or something for a single snapshot, this object's not going to be much bigger than 500K tops. So it's not going to get that big, just because the object is not very chatty in the grand scheme of things. Now, if we started getting to a point where snapshots were approaching, I don't know, 20, 30 megabytes, I might need to get a little creative with how we do that. The other thing that we have going for us is when a user clicks clear screen, this collection gets wiped out. So we stop saving it anymore when a user does that. Let me go back to here, the drawing session actor. This is how we synchronize all of the users' SignalR sessions. Every time a local drawing session actor starts up, they send us a message indicating, if I pull this up in here, they send us a little message saying, hey, I want to get notified about the drawing session. So like, let me know when stuff's happening to this document I'm connected to. So while that's happening, every time someone persists an event, if I scroll back to publish subscribers, every time someone publishes a new stroke, we're going to go and send that out to all the subscribers. That local subscriber actor is going to basically push data into another Akka stream, the second one that I haven't talked about yet. And that's going to drive an async enumerable that causes the SignalR hub to update. So just to make sure we're fully connected on everything, let me flip over to that real quick. But maybe before I do, any questions or comments about the serialization, cluster sharding, the hosting integration, any of that stuff?
Mm. Someone was asking about what if the same user is using parallel browsers, which is kind of what you were showing
Yeah.
earlier, right?
Yeah. So
So each session is kind of a different account. So in your app.
in our case, basically, even though the user IDs are the same, the strokes aren't going to be connected to each other when there's two users drawing. Largely because, honestly, you're limited by how quickly a human being's hand can move on screen there. Our little time-based limiter for detecting different strokes will still chop them up.
Mm-hmm.
So it's smart enough to do that. If you were able somehow to, like, I don't know, like a professional StarCraft player, get like 200 moves per second drawing around screen or whatever, maybe would have a problem. But since my core audience I'm kind of building this for is toddlers, I'm not worried about that level of motor function being an issue there yet. But no, but I did show that earlier, like Maira said, and it works just fine. No problems with that. Let me
We
go
had
take a
an
look.
earlier question, Aaron, which I don't know if you can point to resources in terms of like, I just want to see how a basic aka.net
I got you,
works.
Jose. I got you covered, buddy. So this is another link, and I'll go ahead and message this in our internal chat here in the studio. This is aka.net Bootcamp, and I just redid this a couple months ago, so it's brand new. Supports aka.net 1.5, and it's free to use. So if you click, do Bootcamp, you can sign up via email, or you can click this button down here and just go straight to the lessons. And this is going to have you build a hello world aka.net. That's what these first two units are right here. So it's our first aka.net application. It'll help you build kind of a hello world app, but it'll also explain like, what is this stuff doing from a conceptual standpoint behind the scenes. And then we have this unit down here that helps you build kind of a more sophisticated local application if you wanted to. We're going to add some more units to Bootcamp over the course of this year. My next one I've got planned, I'm planning on starting work on this summer, is we're going to do one on ASP.NET integration with aka.net. And then we'll probably do a third unit on all the fancy stuff I'm doing with clustering right now. That'll probably be in unit 3. But there's a lot of stuff you can do with just local actors in ASP.NET. Good example is like a write-through cache. That's something that I've been using in one of our applications. Our application is high traffic in the sense that it powers a pretty big NuGet server. So when people are doing NuGet package restores, we get hit with waves of requests all at once. So it's not like it's under continuous use, but when use happens, it's very chunky. Therefore, we kind of need a caching strategy that can support that pretty well.
Now with Aspire, will be you should have options
for doing
to cache stuff.
Well, I meant writing a little cache with aka.net where
basically
I can go ahead and run the requests in order. So only the first cache hits only the first request hits the endpoint for that particular tenant. After that, all the ones that occur afterwards, because they might be hundreds all happening like within microseconds of each other, we can go ahead and basically make sure that cached value gets reused. So what I need is a little sophisticated, and aka.net actors are a good tool for doing. There's lots of other goofy stuff you can do with actors too, like running background tasks or doing a little SignalR backplane, doing things like outboxes and all that good stuff. So there's lots of different little use cases for it. But this is where you can go find some good resources on how to build it from scratch. I would definitely recommend checking out Bootcamp. The last thing I kind of wanted to touch on.
Oh, sorry.
No problem.
I was just bringing Philip, which might be related to the bootcamp content, which is like, do you have any architectural diagrams or any visual representation of the system? I think he's referring more to the one for
DrawTogether.
the source code that you're showing, but
so here's what I'm going to do, Philip. I actually did a YouTube video maybe last year that basically breaks this whole architecture of this project down to talk about the client sync and basically the direction which information is flowing. And that's very architectural. I will go ahead and embed that YouTube video in the README of DrawTogether as soon as we're done on the actual live channel here. If that sounds good to everybody. You can find that on the Petabridge YouTube channel right now. It's called Building Real-Time Applications with Blazor and aka.net. But I will make sure that gets referenced in the README here as well.
Okay, that covers all the questions.
Good. So let's talk a little bit about interoping between aka.net and SignalR. That's the piece that's missing right now, is how is stuff actually getting drawn on screen when the server pushes, right? We've seen how events make it from Blazor into the server. We haven't shown how events make it from the server to Blazor yet, right? Let's do that real quick. If I go to my local drawing session actor, I was already had it open. So we get a message that comes in directly from Blazor right here called get drawing channel. That's what this is. And if I go and space this out a little bit, we are going to create a source.actorref with drawing session event right here. Drawing session event means this is an event coming from the server, not an event coming from the local client. So I have different interfaces, one for delineating local events, another for server events. We are going to feed events that come from the server into a system.threading.channel is what we're going to do. And if you're not familiar with system.threading.channels, they're basically a wrapper around a concurrent queue that gives you a nice async enumerable that you can use for traversing all the different messages that are being written into the channel. That's, David Fowler and other people who worked really hard on channels would probably object to that, but that's my layman's explanation for what it is. So it's basically, wrapper around a concurrent queue. What we're going to do is we're going to create a channel reader using Akka streams down here. So we're going to go channel sync as reader, takes a drawing session event, and we're going to materialize it here. So I have a channel reader, and then, let's see, I have a sync for Akka streams, and then I have a channel. And what we're going to do is we're going to take all the events that come into this Akka stream source. We're going to write them out to this channel sync as a reader. And we're going to create a little Akka streams graph. This is basically just some fancy stuff for seeing if the server dies, abort the SignalR updates. That's all that's doing here. And we're going to deliver this drawing channel response back out to the sender. What does that have to do with anything? Well, if we take a look at paint.razor and we look at this little startup task, this little local method right here, I am going to ask for a drawing channel here, and I'm going to get a drawing channel back. And the response that I get back, if I scroll down here, is I get two things from the server. Oh, two things from the actor. Sorry, I get two pieces of data back from the actor right here. I get a drawing channel, so a channel reader, and I get a cancellation token that indicates done reading. And this cancellation token source is coming from, let's see, event stream task. Where does that come from down here? Oh, okay. Yeah, there we go. Good. This cancellation token source is basically something we're going to use to signal to the actor that we are done reading. It's basically what that's going to be. So we're going to get both of these things back. And what's going to happen is I have this little method down here called run data pump. Let's make this full screen real quick. It might be easier to read that way. Run data pump. This is my channel that I got from my actor, and I'm going to call wait to read async right here. So if there's nothing coming from the server, we're just going to await, and Blazor's going to chill. Nothing's going to happen. But as soon as we get some data that we can read, we're going to go ahead and run this wall event stream.tryRead, and we're going to do this until we completely exhaust all the different pieces of data in the channel. And what we're going to go ahead and do is we're going to call handle event. For each of the different events that we can get back from the server, such as users joining, users leaving, strokes being added, strokes being removed, or strokes being clear, we're going to go ahead and update our little data table that we use to manage the visual state of this Blazor application. And then we're going to call invoke async. State is changed right here. This is what's going to actually drive the, Blazor Hub updates. This is going to actually push that data over the wire from a Blazor perspective to actually update the UI. So that's what's kind of causing all that behind the scenes. And so one of the reasons why I like this design is that I don't really want my front end to be dealing with Akka streams and all that stuff. Mm-hmm. I want to be dealing with something that natively Blazor can reason about pretty well, and async enumerable and tasks are it. Okay. So we're basically you could technically turn this channel reader, by the way, into an async enumerable and read it that way. I decided, because it's better throughput, to go ahead and just do task, wait to read async, and then try read. This is basically what the Blazor async enumerable, not Blazor, the system.threading.channel read all function, which gives you an async enumerable. This is basically what that does for you. Difference is I want to be able to hit the invoke async for every single item that comes, so the rendering latency is as low as possible. little bit of front end magic there. So that is the basic gist of kind of what's happening behind the scenes with Akka.net and Blazor. There's a whole bunch of stuff I didn't touch on, like the serialization kits.
But the
there's only
hour flew by.
the hour flew by. There's only so much you can get into. Here's what I want you to be excited about if you stuck with me this long. It's really cheap and easy to get started doing this stuff. You don't need to fire up a VM. You don't need a cloud account. You don't need anything. You can go ahead and clone this and get it all to run locally with .NET Aspire, Akka.net, and Blazor.
Awesome. That was an awesome show, Aaron. Like, it was mind blowing. I love how learning more, and yeah, please go download and see what it's all about. Thank you, Aaron. And next week, we're gonna be back. We're gonna get Hayden Barnes to talk about building cross-platform AI apps. So join us next week. So thank you so much. The community was awesome today. Awesome questions, awesome comments. So see you next week. Thank you.
Bye,
Thank you for your time.
everybody.
Bye.